In Part 2 of this program, we are going to cover acceleration and deceleration of DC motors, as well as how DC drives can regulate the speed of a motor. We'll also cover the troubleshooting methods used with DC motors.
We know that by changing the applied voltage to a DC motor, we can control the speed of the motor and at the same time provide a necessary reduced voltage start to DC motors of a 2 horsepower or more rating.
There are 2 basic methods to speed or accelerate a DC motor. The first one uses a variable resistance, such as a rheostat or resistor bank, and the second one employs a solid-state speed control, utilizing silicon-controlled rectifiers or SCRs. The rheostat method serves the dual purpose of reduced start to accelerate the DC motor to the base speed, which is the speed in RPMs at which the motor runs when full voltage is applied to the field and armature. This variable resistor is used to bring the motor from 0 speed to full base speed. Note that by reducing the field voltage and maintaining the full voltage across the armature, you could increase the speed of the motor above the base speed. In smaller motors, the acceleration can be accomplished in 2 steps by having 1 set of contacts removed after the start, while larger motors will have a smoother start with a 4-step acceleration circuit.
The speed of a DC motor can also be controlled, as we said, with the use of SCRs and a solid-state controller, also called a DC drive. But before we look at this method, let us look briefly at the operation of an SCR.
An SCR, also referred to as thyristor, is represented by this symbol. It is formed by 3 elements, which are the anode, the cathode, and the gate. As you can see, it is very similar to the diode, which is used to rectify AC voltage into DC voltage. In fact, SCRs function very similarly to diodes as far as rectification is concerned. SCRs, however, provide added control through the gates. The gate essentially works as a switch which allows current passing from the cathode to the anode to turn on and off. This control allows the SCR to turn on at any point in the half-cycle rectification from full to partial conduction of voltage. The firing circuit controls the amount of voltage conduction of the SCR by controlling the gate. When used in a bridge rectification circuit, the SCR will vary the amount of DC output voltage. This circuit forms part of a solid-state speed control. As you can see, the power source for the motor is AC, which is being rectified by the bridge in the speed controller and at the same time controls the amount of applied voltage to the motor. As the SCR is fired faster, the voltage will increase, while if it is fired slowly, the voltage will be reduced. These drive systems are usually used in what's known as a closed loop, where a feedback signal, such as from a tachometer, is fed back to a controller, such as a programmable controller, which makes the necessary adjustments to the drive's firing circuit to keep the speed constant if there are any load fluctuations. The electronic circuit which forms a DC drive is a complex control composed of many solid-state components, and troubleshooting it could demand a whole program on its own. Here, we're going to cover some basic points to look for in case a DC motor is not operating correctly and the drive may be suspicious. In a circuit, 3-phase power may be delivered to a DC drive's power bridge. This power bridge rectifies the AC power for use by the DC motor. At the same time that the SCRs rectify the AC voltage, they control the amount of voltage applied to the armature, thus regulating its speed. This control is provided by an electronic control board which controls the firing of the SCRs. If a problem is suspected with the drive, in this case one which uses a so-called 6-pulse bridge, the first thing to do is to check for proper operation of the SCRs, making sure they are firing and providing power to the motor. To do this, you can place an oscilloscope across the A1 and A2 terminals of the motor or from the terminal coming from the power bridge. You should observe this type of curve, where all 6 SCR curves should be present within a 16.66 millisecond range, which equates to 1 pulse for each SCR on each half-cycle of the 3 phases. Make sure the scope is set for at least a 16.66 millisecond scale. All 6 pulses must be present. If not, one of the SCRs is not firing because of a faulty component. If two of the same phases are not firing, it could be due to a loss of phase. This results in erratic motor movements and slower speed. Additionally, the motor will not have a smooth sound, and it will be reflected in its performance. If you are testing or measuring voltages in the drive system, please be extremely cautious because of the high voltages present in large horsepower motor circuits. Also, be aware that the DC motor control board is isolated from the motor power circuit, and the grounds should never be connected to equipment frame or to the AC ground. This will cause extreme damage to the drive control circuitry. Another signal that is good to check and make sure is present is the feedback in this example from the tachogenerator. This tachogenerator provides a DC voltage proportional to the motor RPMs for use by the drive. In the scope, you should see a smooth DC signal providing feedback to the electronic control board, and that there are not large spikes in the system induced by electrical noise.
Just as important as acceleration, if not more, are deceleration methods. Deceleration is used to bring a motor to a complete stop, and it uses control circuits or hardware components to accomplish this task.
Control circuits provide electrical deceleration by causing regeneration of voltage in the reverse direction, while the electromechanical hardware, such as brakes, are used to bring rotation to a quick stop as soon as a motor is turned off. There are three basic methods for decelerating a DC motor: using plugging circuits, regenerative braking, and with electromechanical brakes. The plugging switch, as we know, closes in the forward or reverse position once the direction and speed setting of the rotation is achieved. In a simple plugging like this, the plugging switch can be used to implement a quick stop by reversing the motor once the stop signal has been pressed. Let's see. When start is pushed, the motor will start in the forward direction, and the plugging switch's forward contacts will close and set up the reverse motor to wait for the normally closed forward interlock to be back to its normal state. This will occur as soon as we press the stop push button, which will reset the forward starter coil. At this time, the reverse starter will be energized because there is continuity provided by the plugging switch forward contact, which is still closed by the centrifugal force due to the rotation. The reverse starter will be disconnected as soon as the rotation in the plugging switch slows down close to zero speed. This type of deceleration can also be used in AC motors, except in the single-phase motors which utilize centrifugal switches. This plugging circuit operates in a similar manner, but allows plugging a motor to stop from either direction. The operation of this circuit is left as an exercise for you in the workbook. A slight variation of the plugging circuit is the anti-plugging. This circuit allows reversal of direction once the rotation slows down to a predetermined speed. If the motor is running in the forward direction and stop is pressed, the reverse will not be allowed until the forward rotation slows enough to close the forward contacts in the switch. At this point, the reverse can take place. Regenerative braking, also known as dynamic braking, is used with DC motors to bring them to a smooth stop within several rotations. This method uses, as a principle, the transformation of the motor to act as a generator. A small resistor is placed in parallel with the armature which, when turned off, will serve as a loaded generator that quickly stops the motor due to the reverse magnetic forces created. The braking action of this circuit minimizes as the speed of the motor decreases, and as a result, it cannot hold the load once the motor has stopped. Therefore, friction brakes are generally used along with regenerative braking to help bring the load to a complete stop and hold it stopped. Deceleration of a DC motor to a stop can also be accomplished with electromechanical brakes, of which the most commonly used is the friction brake. The friction brake is solenoid operated and basically works like an automobile brake system. It is connected across the positive and negative terminals of the motor in such a way that if the motor is started, power will be available at the solenoid and the brake shoes will be pulled by the solenoid action, thus removing all friction from the drum. This allows the motor to rotate freely. When power is removed to the motor circuit, the brake solenoid is de-energized and the brake spring is allowed to apply full force to the brake shoes so that maximum friction is created and the motor is brought to a stop. The amount of spring pressure is adjustable through a screw. If set to maximum pressure, the brake will make the stop very quickly as soon as power is removed. If the pressure is reduced, the motor may be allowed to coast slightly before coming to a stop. The solenoid friction brake is generally connected to the motor circuit and rarely to the control circuit to avoid improper activation of the brake. As mentioned a little while ago, the friction brake could be used in conjunction with dynamic braking to hold the load in position. This allows for the brake to have a longer useful life because it can be set without maximum pressure so the brake shoes would last longer. During preventive maintenance, the shoes of the brake should be inspected to ensure that they are not worn out and replaced if necessary. If you need to select a friction brake, it will be necessary to choose it by taking into account the amount of torque of your motor. To obtain this value, you can use the equation of torque equal to the horsepower of the motor times the constant 5,252 divided by the speed of the RPMs at which the motor is operating. The value of the torque will be in foot-pounds, and the brake's torque should be equal to or greater than this value. For example, a 100-horsepower motor running at 1,000 RPMs will need a brake of at least 525.2 foot-pounds.
When a DC motor develops a problem or fault, the electrician or technician must be capable of identifying and isolating the problem quickly and getting the operation back in line as soon as possible. In troubleshooting DC motors, you have either to attack a problem with a series motor or a shunt motor. A compound DC motor is really a combination of the others, and finding its problem is pretty much done in a similar fashion. So let's take a look at how we first approach a series DC motor.
There are two problems that can occur in a series motor which could prevent it from starting. The first one is that there could be an opening in one of its windings or between the brushes and the commutator, and the second one is that no voltage is present at the terminals of the motor. Another problem that needs troubleshooting occurs when the motor is running but still has problems and the symptom translates into overheating. Because the field and armature are connected in series, both coils must operate properly in order to draw a current. If not, the motor can't build enough magnetic field to turn the armature and start the motor. The second cause for the motor not to start, due to no voltage at its terminal, will be due to a line voltage problem in the control circuit, in the power circuit, or in the supply source. In this module, we're going to cover troubleshooting of the power circuit and of the motor itself. If there is no voltage at the terminals and there is power to the starter coil, then check the voltage with a voltmeter set to a DC reading at a terminal point before the power contacts. If there is no power, then you need to check the main DC power supply. If you have power in the supply side of the contacts, then check the load side. If there is no power, then there is a problem with the starter coil and contacts. If there is power after the power contacts, then check at the point before the overloads for voltage. If no voltage is present, then there could be a problem between the supply side of the overloads and the contacts of the starter. Check also to see if the overloads have been tripped. If so, you need to reset them and make note that something in the system has caused them to trip and you need to investigate it. If there is voltage at the motor terminals but the motor is not operating, we can assume that the motor has an opening in its winding or between the brushes and the commutator and the armature. To proceed, you should disconnect the power to the motor and disconnect the series field and armature to test for an open condition. By placing the meter with a selection for ohms to read resistance across the S1 and S2 terminals of the field, we could test to see if an open is present. If the ohm meter shows an infinity reading, then the series field is open, which means that it needs to be rewound or replaced. If the meter reads an ohms reading because there is resistance in the winding, then there is continuity and the series field winding is okay. Regardless of both readings, you should continue the test and inspect the armature, because even if the series field was open, there could still be another problem with the armature. To test the armature, we place the ohm meter between terminals A1 and A2. If the reading shows a resistance in ohms, there is continuity. You should now start rotating the armature shaft slightly so that you can detect possible bad spots where the commutator may have an open or the brushes may not be properly seated. If the ohm meter shows an infinity resistance reading, an open circuit is detected. Continue testing the brushes and the commutator visually for damage.
After detecting an open in the armature coil, you should remove the armature from the frame for repair. The armature can be turned on a lathe by a machinist, and if needed, the brushes can be replaced.
The next problem that we encounter is when the motor is running and gives us signs of overheating or not being able to pull its rated load. Because the motor is running and has proper voltage at its terminals, it is pulling current, and therefore there is not an open in either of its windings. One of the first things to check is to inspect the brushes to make sure they are properly seated and are not damaged. You can also inspect to see if the field and armature windings are loose or damaged, and check the shaft bearings to make sure they are lubricated and not damaged. If not properly lubricated, the bearing could be seizing on the shaft and create friction, which develops heat and reduces its capability to pull the load. Once you've had the motor replaced or repaired, it is important that you monitor again the current and heat once the motor is reinstalled again. The shunt motor also exhibits similar problems as the series DC motor. The two main problems occur when the motor is not running, in which case it could be the supply voltage or its power circuit. If the motor is running, overheating can be exhibited by the motor, thus indicating a potential problem. If the motor does not start and does not make any sound, it is most likely due to a problem with a voltage being supplied to its terminals. Check for a voltage and troubleshoot the power circuit in the same fashion used for the series DC motor power circuit. If there is a loud humming sound, it implies that it is trying to start and has supply voltage present. First, check to make sure that the supply voltage is at the correct level. Otherwise, the problem most likely lies with an open circuit in the field winding. This open circuit can exist if the field winding draws too much current or if a short circuit occurs in the insulation in the coils. To test the field winding, you must remove the shunt connection from the armature. Otherwise, you won't be able to detect an open in the field winding because the armature is connected in parallel and you could read continuity in the armature. Make sure that you remove the power to the motor circuit before starting to test the motor and that you perform the proper lockout after the disconnect has been opened so that nobody can turn on the power to the motor while you're working on it. To test the field winding for an open, we use a procedure similar to the one used with a series motor. With the meter set for ohms, we place the two terminals across the F1 and F2. Make sure that the ohm meter is set to a resistance setting of R times 10K ohms, because the resistance of the field winding in a shunt motor is high, due to its winding being formed by a very long wire. If the reading from the meter shows resistance, then the field winding is good and has continuity. If the reading shows infinity resistance, then the field winding has an opening, and the motor must be repaired or replaced. The armature should be tested next by placing the ohm meter across the A1 and A2 terminals. If there is a resistance reading, the armature is okay. If it shows an infinite resistance, the armature has an opening in its winding. Make sure you also check the brushes and commutator to check for damage and see if the brushes are worn out or not properly seated. If the commutator is damaged, you can have it turned down in a lathe by a machinist. If the armature has an open, you must remove and replace the motor. In some cases, you may be able to replace only the armature without removing the whole motor. Note that when taking a resistance reading in a shunt motor, the shunt field winding resistance will be much larger than the armature resistance. Conversely, in a series DC motor, the series field winding resistance will be less than the armature winding, since the series field is made of large gauge wire. This small detail will help you identify which wire belongs to which winding in a DC motor. If the shunt motor does run but heats up or starts to draw too much current, it should be tested for a loose coil or a shorted coil in the field and armature winding. A loose field can cause the motor to vibrate and overheat and should be checked during preventive maintenance to ensure that they do not come loose. The same applies to the armature. The compound DC motor, as we know, is a combination of the series and shunt motors, and its troubleshooting should be done using the same methods as the ones used in the series and shunt.
In this module, we have covered some important information on how to control the starting speed and direction or rotation of DC motors, as well as the ways to troubleshoot them. It's important to always remember to tackle a troubleshooting problem from the top by listing the areas which are giving us the symptoms of the abnormal operation. In this manner, we can find and solve the problem. Keep in mind that if a motor had a problem or burned out, simply replacing it is not a solution. We must know what the reason was for the failure. Otherwise, our new motor will fail again.